we'll cover the algorithm that I talked about earlier, the breadth first search. So this is an algorithm that what it does is it solves the unweighted shortest path problem. It can solve it for directed or undirected graphs, as we'll see. And, you know, whether it's directed or undirected, it's not going to change the algorithm much at all. In fact, as you'll see, the algorithm just operates on the description of what the adjacency list is. And we already saw that adjacency lists are just different for directed versus undirected graphs. Like when you build the adjacency list, it'll have a different content depending on whether the graph is directed or undirected. And that's basically going to be the only difference to the algorithm. So what is breadth first search and how does it work? So first of all, you know, the nature of the problem is that, okay, so, you know, we have some kind of graph. You know, just let's pick some like abstract looking graph. And, you know, we have some nodes. And this is the unweighted case where we're not going to put any weights on these. We're just going to keep it simple. Essentially, every weight is 1. And we want to find the shortest path from one place to another. So, for example, you know, like if we have something like this, we would, and let's say, you know, we given a source node, given like a starting node, source node, as it's often called, and the destination node, we want to find the shortest path between the two. So here there are many paths from A to E, right? But our algorithm will have to discover the shortest one. Like, you know, this is the shortest one, right? A, B. But, you know, A, C, D, or A, F, G, D are also possibilities. You know, maybe there's even a link like that, but it doesn't, you know, this is still the shortest path. So it's actually pretty intuitive to understand how breadth first search worked. When I first learned this algorithm, like actually, it was described to me as flood fill, which is a good way to understand how it works. So it's kind of like a physical analogy. So the idea is, you know, you take a pitcher of water and you start pouring it on A. And in 1 unit of time, the water spreads to each adjacent vertex. And then we're basically asking how long does it take to get to E? And that will essentially determine the shortest path. So, you know, so for example, at the first step, at time 0, we have this vertex filled with water. And now what we want to do, and you know, hey, this is why adjacency lists are so useful. We want to get all the neighbors of A and flood them as well, and they get flooded at time 1. So, you know, we'll see like the exact implementation of this, how it would work, but this is just at an abstract kind of conceptual level. Oh, sorry, not 1, 2, 3. Why am I counting these? It is 1, 1, 1, of course. This marker is not very useful. Okay, but anyway, yeah, so at time 1, all of these neighbors get flooded. Okay? And then at time 2, any additional neighbors of those neighbors would get flooded. So, like already the water is flooding out. At time 1, it's reached all of these vertices, and now it's kind of expanding outwards in kind of this increasing wave front. So anything that is touched by, you know, one of these nodes that's already been flooded is going to get flooded on the next cycle. So, you know, for example, this node is going to be 2, but so is this node. And then so is this node. And once we see that our destination node has been flooded, we can actually stop. So there's 2 kinds of BFS that, you know, this is called BFS, breadth first search. I'll talk in a moment about like why it's called that. You know, sometimes also known as flood fill, you know, because of this analogy. And, you know, there's 2 kinds of like common uses of BFS. Like sometimes, basically, you want to find the shortest path between a specific source and a destination. So here we can just stop as soon as the destination node is flooded. But you might notice that this algorithm is actually computing, starting from the destination, the shortest path to every node in the graph. So if we just let it keep going, if we were to just, let the algorithm continue, like for example, let's say, well now all the nodes are flooded, so the algorithm stops. But let's say, there were more nodes in the graph, for example, there's this F. Well, now, now F can get flooded at time 3. So this algorithm can also be used, not just run until you find the node you're looking for, but it can be used to find the distance from the source to every other node in the graph. And the concept of distance is basically defined in terms of the length of the shortest path. We say that there is a distance of k between two nodes if the shortest path between those two nodes is of size k. Has k, has cost k. And in the version of in the unweighted version, the cost of a path is just how many edges it has. So conceptually, this idea is very simple. Hopefully it makes sense. So you start flooding from the source node, and then you just kind of you expand out in what's called a breadth first way, and you expand out to all of your neighbors, not just one of them, right? So there's if you study trees, you might remember depth first traversal, which is the same as a regular, that's a typical tree traversal, post order, pre-order, all of those are depth first traversals, where you pick one branch of the tree and you go down it, and eventually you do something on your way back up, right? If you haven't really studied trees, it's not actually that important to this, it's okay, don't get confused about it, but if you did study trees, you may remember that most tree traversals are essentially depth first. There was essentially also what was called a level order traversal of the tree, right? Which is the same as kind of this concept. A level order traversal of a tree is, the same as breadth first search, except here we're doing it on a general graph and not just on a tree. So we're kind of going level by level, except here there's no in a tree the concept of level is kind of better defined. A graph, it doesn't have any root or anything like that. So the levels are just defined in terms of how far they are from where we started. So this is level 0, then these are level 1, then the next wavefront is level 2, which is out here and here, and here, and this is level 3. So a couple of points to be kind of aware of here. So we started by marking this with 0, and then we marked this with 1, right? So imagine the point where we got up to here, right? We got up to here. One thing to be careful about is that when we, further expanded the wavefront, we must be careful to mark with a new distance only nodes that haven't been visited yet, right? Because if we say here, and then we say, oh, look, A is a neighbor of B, so it must have distance 2, right? That would be wrong. So the point is, you only expand the wavefront out onto nodes that haven't been visited. So you start with A, then you expand out to these, and then you look at the neighbors of the nodes you just discovered, because they're your newly discovered nodes, and you look at what neighbors they have that have not been visited yet. And then those are the ones that are visited at the next step. Okay. So conceptually, we can see this algorithm as advancing in stages, right? One way to think about it is, this algorithm advances stage by stage. So there's the initial stage, we'll call it stage 0. So stage 0 is complete just at the initial setup of the algorithm. That just involves marking A with 0. So, this is basically, now I'm kind of getting a little more, that was the conceptual explanation. Now I'm getting a little more closer to how it will actually be implemented. And then we'll actually see in a lot of these sessions I don't do pseudocode for stuff, but for this one I think it's valuable to basically see the pseudocode for this. And we'll see that in just a second. But the initial kind of stage of this algorithm, just here, let's refresh it. I might draw a different graph this time, it doesn't really matter. Okay. So, the initial stage of this algorithm just starts out like this. We basically think we visited only node A, and we visited all the nodes at a distance of 0 or less. And our goal is, given the nodes at distance 0, we want to discover the nodes at distance 1. So basically next we're going to discover, like, this is what we had before, and now we're going to discover this additional tier. And we're going to mark these as 1. And then we want to visit all the nodes that are, neighbors of the newly discovered nodes that are also not visited. So we're not going to go back to A, because, the water is flowing from that direction. And also if there's links, there can be links between nodes at the same level. We're also not going to do anything with those. This doesn't get marked as 2 either. But anything that's unvisited, we're going to go to. And so the algorithm is just going to progress stage by stage. And at the kth stage, we're basically going to already have all the nodes that are distance k away or less, and we're going to produce newly the nodes that are distance k plus 1 away. So, the next iteration of the algorithm will capture these nodes. And then if there was another node, down here, then the next iteration of the algorithm will capture that. Okay, so let's see how, it's a pretty simple idea. So let's just see kind of how it works in terms of pseudocode. It's actually, pretty easy to just jump right into. So we'll assume that our nodes are stored in an adjacency list, and here you will see why, it's good to have your nodes in an adjacency list. It's because every node will need to know about what its neighbors are for the purpose of flooding outwards to them. So, okay, so let's see this. So we will basically need, first I'll show you kind of one draft that's based on the conceptual idea, and then I'll show a small optimization, which is the usual form you see this algorithm. It's just a small simplification that you will see later. Usually you see this algorithm implemented in terms of what's called a queue, and you'll see why that is. But right now we're not going to implement it using a queue. We're just going to have 2 list variables. One is going to be called past. So past is basically the past tier. So initially this starts out initialized with just the source vertex. So I'm going to use kind of a Python-y pseudocode. This means it's not meant to be exactly Python, but it's like a Python-y pseudocode. This is just a list initializer, basically saying create a new list that has the source vertex in it as the only element. So this is just the overall function definition. So define the function, shortest path, and shortest path, and you got source, and you got destination. Except here, here I'm not even going to put this, the destination. I'm just going to do the version where you find, you find the distance to every vertex, and I'll tell you how to modify it to just, it'll be trivial to modify it to just stop as soon as you found the one vertex you actually care about. But in many cases, you care about all of them. In many cases, you want to find the distance between a vertex and all other vertices. So, I'll just pass in a single source here. And of course, I will pass in the graph. Let's say for now, the graph doesn't have any weights and it doesn't have any data other than just the adjacency list. So this is just going to accept the adjacency list. And the adjacency list is, say, here it's just in this format that, it just kind of has that format we discussed earlier. Formats that look like this, So this adjacency list is basically like a map, mapping vertices to their, basically mapping vertices to the adjacency list. Okay. So initially, first we kind of have this past tier. This is the last tier for which we have known computed distances. And this starts out with the source vertex because that's the only vertex right now whose distance we know. The source is a distance of 0 from itself. And then we have, we'll call it current. And this is an empty list for now. Current will accumulate the nodes at the next distance level. So in other words, we'll accumulate nodes of distance 1 into this list initially. And then, we'll have, well, that's all we need for now. One more thing we better initialize right away. This will just be essentially a map. This is going to be a map that is basically the results we're going to return. And this is basically going to be a map that for, in the end, what we want to return this map, and what we want it to contain in the end, is it should be a map that maps node identifiers to their distance. So for example, if we started at A, this map will contain A to 0. So at first we initialize this map with this data. So this means, this is like value and key. So with the distance map, we're just initializing it with source has a distance of 0. At any given time, we're going to maintain the invariant that this contains only the known distances. So like this, at any given time, it will contain all the distances that are currently known. And the algorithm will continue trying to discover new distances until it's out of nodes to explore. Okay, so depth, shortest path, past, current, distance. Okay, so now we should do something while while not past is empty. And what is this line of logic? So this is just to prevent us from doing stuff once we've run out of elements in past. If at any given time the past here showed up no elements at all, then we are done because there's nothing more to do. Because the next thing we're going to want to do is basically loop over everything in the past. So if it's not there, then note that past is only like the one past level. It is not all nodes that have been visited so far. If you want to know all nodes that have been visited so far, they're here. But this is just a past level. So initially these are one and the same, but like basically these at any given time, if we're currently discovering the nodes that are at distance k, the past list is the nodes that are at distance k minus 1. If we're currently working on discovering all the nodes that are distance k, this is the nodes at k minus 1, and these are the nodes that are at k. And these are all of the nodes whose distance is known so far, which must be distance k or less. Okay. While not, past is empty. Okay, so now what we want to do is basically, we want to loop over each node in the past. So for node in past, so loop over all the nodes in the past. And for every node in the past, we basically want to loop over all of its entries in the adjacency list. So here we have a node A, and let's say it's our starting node. And let's say node A is connected to B and D. These are the nodes, we want to take node A, and we want to loop over these nodes, and these are going to be added to the current variable. These are because, A is at distance 0, this is the only node that's known so far, and, we're going to mark these nodes as being at distance 1. We're going to flood them. Okay. So, again, this is just a loop. For, we'll call it neighbor. I'll abbreviate it to na. For neighbor in what? Well, we have to get this list from the adjacency list, right? So this is easy. In adjacency list, access node. So, this just uses node to look up this in the adjacency list. Okay, and so now these are these individual elements. And so what do we want to do for these individual elements? For all of these nodes, we want to see if they're already visited, right? This is important. We can't just mark everything. Because we have to make sure that, if, for example, we came from A, and A was marked at 0, we came to B, and B was 1, and now we're going out to C and D, we have to make sure that we only mark C and D to 2, but A might be a neighbor of B too, right? But we don't want to mark A as 2. That would be wrong. We don't want to revise any distance that's already been put in, right? So we want to check if it's visited. Okay, so we have to check if it's in here. This dictionary should at any given time contain any nodes we have seen thus far. So far, we're seeing this node for we are processing this node, we're exploring its neighbors, and some of these neighbors may be already visited and some may not be. We're exploring these neighbors, A is already visited, but now, C and D are not, and we're going to mark them. So, what do we do here? Well, we need to do if. We want to say, if neighbor not in the distance map. If it's not in the distance map, then this is a new neighbor. This is basically saying, like, if distance does not contain the key of neighbor, that's what this is saying. So if neighbor not in distance, then add it to the distance map. So distance map of neighbor. And what should the distance map of neighbor be? Well, it should be the distance of the node plus 1, right? If we're flooding out from a given node and we're exploring its neighbors, and this is a node we're processing right now, then the neighbor has distance 1. If the neighbor has not been visited before, then, like if this B had distance 1, then this C and D had distance 2. So it's whatever the distance the node had plus 1. Alternatively, like, we don't even have to access this, we don't have to access node from the distance map here. You might note that it's true, like, based on this, like, tiered approach we're using, it is true that all the nodes that are in this list have exactly the same distance. So we could just keep a variable in here. All the nodes that are discovered here in a given iteration of this while loop are actually going to have the same distance here. So we could keep that in a separate variable, but it's going to be more convenient to just kind of do it like that. Node plus 1. This is distance. Okay. And then we need to do something else too here, right? It's not enough to set the distance. We must also put the distance in this map. Not in this map, in this list. And why is that important is because if we just discovered C and D and gave them a distance of 2, it's possible that C and D have, like, further things we need to do for them, right? We now need to explore the neighbors of C and D in turn, because they might lead to more nodes we have not discovered yet. Okay, so that means that current, like, we're going to do, like, current dot append. We're going to append to the current list the neighbor. Okay, and then that's it. We note that something can only, any particular node can only get added and processed once. The reason is that because this is the only place we ever add to a processing list, but if this line is hit, then this line is also hit, which assigns the distance and makes this condition not possible again for that same node. So every node will get processed exactly once because we're basically saying, if you haven't seen this node, then immediately mark it as seen and assign it a distance, and then it can never be unvisited again, and then put it in the queue for processing. So, put it in this current list for processing. Okay, and so now as we iterate through this, we will fill up the current list with all the unvisited neighbors of everything in this past list. Then the only thing to do is, once we've processed everything in the past list, so now we're coming down to this level of indentation, we have to basically, for the next iteration of the loop, we should set current, we should actually set current, or we should set past to be current. So swap the lists, basically, set the past to be current, and set current to be a new list. And then eventually this condition will be hit. Eventually it'll happen that nothing will be added to the current list. It'll get assigned to this past list. The past list will check, will test this condition. And eventually, like, we are done here. If this condition falls through, then we are done. And here you're just going to return. And here we're just going to return the dist. I know for some people sitting in the back, maybe you don't see like this lowest part of the board, but this just says past equals current, current equals empty list, and return distance once this loop falls through. Okay, so this is like, this is like all there is to it. It's a pretty simple algorithm. You start with a past list that you start with all the nodes at distance 0. And what is happening here is every iteration of this loop is finding all the nodes at the next level of distance. So we start with just the nodes at distance 0, and here there's only one node in this list, source. And source gets processed, and we find all of its neighbors. And we go through all of its neighbors, and we assign a distance to them. And then we append them to this current list. And then for the next iteration, we assign the current, when we're all done, when we're done accumulating the current list, we assign the current list to this variable for the next iteration. And this list starts out clean again. And then in the next iteration, you'll go through all of the nodes that were at distance 1, find all of their neighbors that have not been touched yet, and assign them a distance of 2, and put them in this list. And then the next iteration will go through all the nodes that are at distance 2. The next iteration of this loop goes through all the nodes that are at distance 2, goes through all of their neighbors and assigns them a distance of 3 and puts them into this list, and so on. And, eventually you will not find any more neighbors. Current will be empty. It'll get assigned over here, and then this condition falls through, and you will return. So, okay. So this is like the basic core algorithm. This is kind of, a simple implementation. Any questions about this before I show kind of like a small optimization, which, it just kind of cleans up a couple lines of code. It's not really like a big deal. I think it's easier to understand this in terms of like, first you find all the nodes at distance 0, then you find all the nodes at distance 1, then 2, then 3, then 4. But you don't have to think about it that way, and that's what the optimization is about. But any questions about this kind of initial idea first? Okay. One simplification you can make is you can basically say, well, look, you don't really have to keep past separate from current, because what we can do is we can just append more nodes onto the end of past. And as long as we're appending to the end of past as we find new nodes, like basically just any nodes you want to put in here, append them to the end of this list. And then, if that happens, then you don't have to work, it's still true that all the nodes in past are going to get processed before any nodes you've inserted into current, because you're appending these to the end of the list. But then you kind of don't have to do the switch of lists. Then just basically, as soon as you're done processing these, now you'll have appended some nodes here, right? They'll start with these ones, but while you're processing this, you'll append some here. And as soon as you're done with all the nodes in past, you'll already start on all the nodes that are coming from current. And then when you're done, and then as you process those nodes, you're accumulating even more. And so this can be seen as a queue. So again, if this step confuses you, notice that this is just an optimization. There's nothing wrong with using just the step-by-step notion of the algorithm, where there's actually no there's no asymptotic efficiency difference or anything like that. This is just kind of a small optimization. So the idea is you make it a queue. So we'll call this Q now. Call it Q. And Q is literally a Q. Not the letter, but the Q. And, so Q is basically a new Q of some kind, and then Q dot NQ. And this is at the same level of implementation as everything else, just in case you're wondering. And Q dot NQ, the initial element. So now you only have one list instead of 2. It's just going to clean up a couple lines of code here. Otherwise, not particularly important. So what does it clean up? You still need this distance map. So instead of while not past is empty, while not Q is empty. So as long as the queue is not empty. But now, we don't have to loop over every node. We'll just take one element from the queue at a time. So here we're going to do. Here we're going to say node. The current node that we're processing is q.dq. So basically take something from the front of the queue. Take the next thing in line to be processed. And then, this block was indented before, but now it's at the same level as this. These are at the same level now. Now you have, you still have to fetch its adjacency list, for neighbor in this, check if neighbor's in distance, and instead of appending it to current, well, you append any neighbors you want to the queue. Then there's no need to do this switcheroo here at the end, because you're just going until the queue is empty, and the queue is already being removed and enqueued here. You still need, of course, this check. You have to make sure you're not processing any nodes that have already been processed. These are all, these two statements are at the well, okay, I'll rewrite it a little bit so it's clear. These are completely at the same level of indentation. And then finally here we would return. Okay.
That will be q dot nq, right? Instead of append.
Yeah, sorry, you're right. Yeah, I forgot to change the method name, yeah. Q dot nq. And I also called my q the letter q, but whatever. Okay. Q. Yeah, this is q dot nq. I specifically made it one letter to make life easy for me, and then I didn't do it. Okay, well, yeah. So this makes it even simpler, like you just manage everything through one list, but this is essentially just the observation that if you manage everything through one list, it's kind of the same as if you were doing it step by step. Right, the ordering in which you process things is definitely important. Like, you don't want nodes that are at distance k plus 1 being processed before nodes at distance k. That would potentially be bad. Because, then if you examine a node that is a distance k plus 1 away, and you haven't yet examined all the nodes that are at distance k, then if you find a neighbor of the node that is like, so here's my source, here's a node I'm examining, and let's say this is a distance k plus 1, this is like dist k plus 1. Problem here is, if I still have nodes that are a distance k away that I have not examined, I might incorrectly conclude that any nodes I find here, A, B, I might incorrectly conclude that these are a distance k plus 2. I might label them as k plus 2, because this one is k plus 1. But that might not be correct, because, it could be that there's another node that connects to them that I haven't scanned yet, and this one is only a distance k, and then these are actually a distance k plus 1. If there's some other n2 here. So that's why it's important to process nodes in order of distance. Like, this algorithm only works if you process nodes in order of distance. It's important to understand that, but you can just see here that because you're always appending to the end, it's guaranteed that all the things that the first distance will get processed first, and only then we're going to start processing things at the next level of distance. And then when we're done with all of that, we're going to process the next level of distance. And only when we run out of things to process does this condition going to happen. Return distance at that point. Now, of course, there's nothing stopping you from putting a condition, right? You can put a condition somewhere to basically say, like here, you could say if neighbor not in distance this, and then after you do the step, you could say, if neighbor equals destination, return distance of destination. Right? So it's easy for you to terminate the algorithm early. This finds the distance to all of the nodes from the source, but it's easy to terminate this early. Okay. So it's easy to terminate this early, but how do you recover the actual path, right? Because sometimes, for some applications, you might actually want to know, what is the path? Not just it exists or it has distance 4, right? But how can we trace back the path? Well, good news, this is actually really simple. So instead, what we can do is instead of just storing an expression like this, which is just a distance, we can actually store pairs. In the distance map, instead of mapping it to just 0, we can map it to a pair, like this is a 2-tuple, that has a distance. And it also has, what I'll call an origin vertex, basically where you came from to get to this point. So initially this is null, because you started at the starting point, you didn't come from anywhere. This one, the vertex at distance 0 is the only one that will have, null here. Okay. So now here, when we assign this, we want to assign it to a pair. And the pair that we'll assign it to, the pair that we're going to assign to is going to be, it's is going to be the distance first. So we have to get, distance of, we still have to get distance of node. And then distance of node is now a 2 pair, so get the first element, dot d, or whatever, call this first field d. And then the second element here is just going to be the node itself. So in other words, what we're doing here, like these parentheses, like this is kind of Python-y syntax. This means like construct a tuple that has these two. Construct a pair of elements that has these two entries. In Java it might look like, new pair, whatever, like, new pair, and then like 2 arguments or whatever. Right. It depends on your language, but this just means we're constructing a pair containing these 2 things. So in distance of neighbor, we are storing these 2 elements, or we're storing a pair containing these 2 elements. So we're getting distance of node. We're retrieving the node's record and we're getting the distance, and then we're also putting the node here. And that basically just tells us that we discovered the neighbor through the node. Why is that useful? Because eventually, like let's say we ran our algorithm, and eventually the algorithm did some things, and eventually we came to the destination. Right? Now what this destination has in this distance map is it has a record that is basically saying, well, okay, first of all, you are 3 steps away, but it also has an element that basically tells it about this node that it got here from. So, if this is A, B, then this has a record that in the distance map, this is storing a record like 3B. And this one is storing a record like 2A. And this one is storing 1 source. And this one is storing 0 null. So now what you can do is once you find the destination, or if you found it for all nodes, then just you got this information for all nodes. Now just anytime you want to trace back a shortest path, you just follow these links back. Like you take this B, then you look up in the distance map and you get this. And so now I'm just kind of inserting into a list. I'm inserting dist, I'm inserting destination, then B, then A, and then source. And then this is just a reverse path. And I can just reverse this list and it's my path. Does that make sense to everyone? Like basically, hey, if you want to trace back the path, one easy way is augment with extra information. Maybe you don't like this, maybe you just want to keep distances in here. Or this should have been like +1. I dropped the +1 when I did this. You can keep distances in here. You can make like a second map. You could make like another map called traceback or whatever, and you could use that instead of keeping pairs in this map. But alternatively, you should just keep pairs. And so basically every node knows about its distance and also what it came from. It knows what node it came from, and then you can just use that information to trace back. You take this 3B, you look up this B record in the distance map again, you get this result. You look this up, and trace back until you see this null. It's very straightforward procedure.
The second element, right, from where it is came from, it can be a list also?
No. It can't be a list. Like the question was can't it be a list? No. Every element comes from precisely one source. This is, for every element what we are putting in here is where the one node that it came from. Remember, this condition can only happen once for a particular node. Once this condition hits, this is assigned, and then this condition can never trigger for the same node. So, every node basically has a unique source that it came from. Every node was discovered through a particular vertex, and only from one vertex. It was the vertex you first explored to get there. Now, it's true that which vertex that is may kind of arbitrary, consider an example like this. And then if you ask me, from which vertex we will discover D? It is whichever one we happen to process first. So A will discover B and C, B and C will definitely be discovered from A in this graph. Well, if A is the source. If A is the starting point, then B and C will get records that look like 1, comma A. So A has a record like 0, comma null. B has a record 1, comma A. C has a record 1, comma A. D's record will definitely be 2, but will it have B or C? Well, it actually depends which one just is processed first. If B is processed first, then B will be the one to find D. But if C is processed first, then C will be the one to find D. And it's arbitrary, and it's because it doesn't matter, right? It doesn't actually matter if it's B or C. Like, either one leads to a path of size 2, so it doesn't matter.
But it wouldn't matter if the edges are weighted.
Yeah, the question was would it matter if the edges are weighted? Well, this algorithm doesn't deal with weighted edges. And, if you have to deal with weighted edges, the modification that you need is bigger than just changing something like that. Yeah, essentially there's an algorithm called Dijkstra's algorithm, which is a little more sophisticated. It is essentially just a generalization of this algorithm, but it's, as we'll see in the session on Dijkstra's, which will be, held in, I don't know, maybe next month, we'll see. As we'll see in that session, Dijkstra's algorithm has some extra steps. It's not as simple. There's a lot you have to change when you change to weighted edges. Yeah.
The D+1 on the third line from the bottom.
Oh, like what is the distance of neighbor? It is the distance of the original node plus 1. It's taking this field. It's like a pseudocode thing. I mean, it's like, okay, technically, in like something like Python, this would be like brackets 1. I just don't want to, or brackets 0. I don't want to use that notation then. Like this is looking up node in the distance, and then you're getting this tuple, right? And you want to access this first field. Yeah. Yeah, alternatively, you could put these in different dictionaries. You could have a distance dictionary, and you can have like a traceback dictionary. Okay. Any more questions on this? Yeah, weighted is going to be a different algorithm called Dijkstra's. Like, it takes a little more. It is a generalization of this, but it takes a little more effort to get to solve this problem for weighted. This is just for unweighted graphs. Does this work for directed and undirected graphs? Like, sure. Actually, like, there's no modification needed here for directed or undirected graphs. The only thing that changes based on whether the graph is directed or undirected is what's in your adjacency list in the first place, right? Remember how the adjacency list should only have the edges you can actually follow in the correct direction. So that's all that has to change in order to make this algorithm work for directed graphs. Like, you just have to set up your adjacency list, right? And then after that, it's the same algorithm.
Would there be any efficiency benefit of having the distance map in the adjacency list? Just kind of have an empty field there where you just plop it in? Then you don't have to create this thing that's kind of permanent.
I mean, sure, but like that's if like the adjacency list you're past already has space for that field or whatever. Yeah, I mean, sure, like maybe you could have it stored right in here. But that really seems like a micro-optimization. Okay, so, this session is just about over. We're just about out of time. I do want to, take, just 5 or 10 more minutes. I want to do, one really simple problem involving breadth first search. So we don't have time for a more complex problem like a node. So the next session, will actually have some time that will just be dedicated to seeing some, slightly more challenging breadth first search problems, problems that are just solved using breadth first search, but are still maybe a little tricky to figure out how to set it up. But right now we'll just look at a simple one, just to illustrate one important aspect of breadth first search that is important to understand. So this, when I pick problems, I don't just pick the hardest problem or the most fun sounding one. Often I pick problems that because they kind of have a lesson to teach. So let's think about this problem. Okay, so there's a number of bus lines in a city. So, imagine there are stops along the way, right? So, this is a bus line with stops along the way. And some stops are maybe places where multiple buses stop, right? So, here's some bus lines. And basically what I want to figure out is, given a source and given a destination, what is the minimum number of buses I need to take to get from one place to another? So already this sounds like a shortest path, because it's about how many lines I have to follow before I can get to a particular spot, and it's clear that it's all about like the connectivity and whatever. So it should be pretty clear that this is like a shortest path problem. But there's one complication here that we'll see. So the problem is, so everything is. So what's kind of the obvious way of representing this, right? What's the like obvious idea that comes to mind? Well, obvious idea is that we should model each bus line as an entity, right? Because the shortest path question we're asking is about the number of bus lines. If we were asking about stops, minimize the number of stops, then we would want to model it kind of as it's depicted here. We would want this to basically be the graph if we were looking for a number of stops. But we're not looking for a number of stops, we're looking for a number of bus lines. Right? How many times do you have to change the line? Like, you don't care about stops, right? Because you just kind of get on it and you forget, but you don't want to switch buses, maybe. For example. It's maybe a little of an artificial problem, right? Okay, so, these are just labels I'm putting on the bus line. Like, this is line A. This is line B. This is line, this line is line C. Alright, I'll put it on here, since we can't get confused. This one is line D, all of this, and then this one is line E. And now, the idea is, I'm going to give you two stops, and I want you to tell me the smallest number of bus lines you need and which bus lines they are. So because this is being framed in terms of bus lines, it seems pretty clear that I should model those as entities. So we should have entities A, B, C, D, E. So let's do that. A, B, C, D, and E. Okay, when should two lines be connected? If there's a common stop, right? So we'll look through the stops of every, of all the lines. That itself, we'll have to be careful to do efficiently. What we don't want to do is we don't want to take line A and check it against every stop to line B, right? The smart way to do this that's efficient is basically build a reverse lookup of the stops. Like, in other words, go through all of the stops of A, and basically this is like S1, S2, S3, S4. Build a map that is like S1 is at A, S2 is at A, or whatever. And then basically find out if like any lists have overlapping stops, and so give them edges or something. That might be a lot more efficient than just trying to compare every line pairwise, because there could be a lot of lines, and each individual line could be long, and maybe that won't be linear time or something. Okay. So now you're at this situation. So now we're going to draw like these edges here. Because A and B share a stop in common, like this stop. So we're going to like connect A and B. And B and C is going to be connected. Well, okay, I need to make this a tiny, bit more interesting maybe. Let's say, let's say this line like, loops around and also connects here. Okay, well, sure, why not? Right? Like, real lines do that all the time. Okay, well, so then, C and D are connected. D and E are connected, and C and E are connected. Okay, so you have something like that, right? Okay. So you have this connectivity graph. And now with the formulation of this original question is I'm going to give you a source stop and a destination stop, and I want you to find how many lines are necessary. So things are fine and dandy as long as I give you something like this. If I tell you like this is the source, this is the destination, then it's easy. This stop belongs to line B, and this stop belongs to line D. So then it's just shortest path between B and D, the solution is 2. Okay, so you need to take the B line, and then you need to make, like, it's going to be the number of switches, right? That's what's being calculated here. Like you need to take the B line, then you need to switch at the C line, and then you need to switch at the D line. So it's a total of 3 lines, but it's 2 switches, and then that's why the shortest path is 2. Add 1 if you need to output 3. Okay. So, as long as a stop belongs to a particular line, this is easy. Just, abstract the lines away and then shortest path. But, you guys see the problem here probably, right? Which is that, what if this happens? What if a line belongs to multiple things, right? Or what if a stop belongs to multiple lines, right? Okay, so first attempt at a solution, right? We can just try every possibility. This can be line A or line B. Let's just try both. And this can be line D or line E. Let's just try both. So that's only 4 possibilities, right? So basically we'll consider going from A, we'll ask what is the shortest path going from A to D. Well, then we'll try A to E. Then we'll try B to D. And we'll also try B to E. We'll consider all of these options, and we'll pick the best one. This makes sense. I mean, this is like you're just, you have 2 choices at the beginning, and you have 2 choices at the end. For each choice, we can find what the best path is, and then just take the best one. The problem is what if this is like a bus terminal, and there's 50 buses here, and there's 50 buses here because this too is a terminal, right? That actually could be a common use case. Then we'd actually have to try a grid of 50 by 50 possibilities, which is maybe not ideal, right? Okay, so good news. Basically, BFS handles this almost without any modification. You just have to know how to use this right. So first of all, let's consider a slightly simpler case, which is you do know where you start, but you don't know which one you end on. So this basically requires almost no modification to BFS whatsoever. Because basically you just start, you would start flooding outwards from the B vertex, and you would just have it as your stopping condition that whichever, you basically have a set of lines that you want to end up on, so you have some set that contains D and E here, and basically you will just have a stopping condition there, the same stopping conditions I showed you before for the destination. Now you will say, if this vertex is in D or E, return it now. And so without any modification, just a trivial change to the stopping condition, we'll stop at whichever one we see first. So we'll find the one to the shortest destination. Now this one's a little bit trickier. How do you handle the fact that, okay, so already we've improved, right? Because already, even if we have a case like this, maybe we still try every possible starting line, but now we only run one version, one iteration of the algorithm for every starting line. So if there's 50 starting lines in this terminal, 50 starting lines in this terminal, we run the algorithm 50 times, but not 50 by 50 like we were doing before. But the news gets better. So it turns out this works without almost any modification. If you just label 2 nodes with 0 marker, BFS can actually do this. You can just label both of these with 0. The only condition is you have to put both of these in your distance map. So when you initialize, you will not put just a single node in your distance map. You can put all the nodes you want and set them all to 0. So we'll initialize our distance map with the set of all the lines that stop here, and mark them all as distance 0. And then we'll flood outward from both of these. And this actually works. So when A floods outward, it just floods to B, but B is already marked as 0, so this doesn't get a 1. And then B floods as 1, and then D and E flood as 2. So this actually works just fine. And if it turned out to be the case that, let's say this A line is actually now, let's say it's connected here to this E line, right? Well, let's say there's another line that connects them, right? So, this is just to show you how this works. So this is, let's call this line the F line. So in other words, we're saying that there's now this F line passing through here that A is connected to, and that is also connected to E. So, how will these distances be found? Well, start out at 0 on both of these. So both of these start flooding out at the same time. You're like pouring pitchers of water on both of these, right? And this gets marked as 1 because it's flooded from this node. So this kind of has information like 1 comma A, like 1 source of A. And then this one gets like 1 what source of D. And then, this one, like, it could get flooded from C or it could get flooded from A, but the point is like, we will get like a 2 comma something, 2 comma F or whatever here. And, D will also be visited, 2 comma C. This is like the distance and the traceback information, and this works perfectly fine if you just start with a set of vertices rather than one vertex. If you want to kind of try to like sort of find like the formal proof that this works, I mean, I'll leave that as an exercise. It's not like terribly hard to show that this works. Basically what is, like we should be sure we understand, like, what is the meaning of distance in this case? Distance is the distance to the closest of the origin points. Like, if you have multiple departure points, multiple sources, then any distance found by BFS is going to be the smallest distance to any one source. So here we're just going through, and for every destination we're saying, what is the closest to any, what is the closest to any one of the possible sources? And, we find this for all the nodes, and then, whichever one we reach first is the one that we take. Okay, we're definitely out of time. We're a little past time. Well, I want to thank everyone for coming. The next session will involve some more complex BFS problems, and we will also cover, probably Dijkstra's algorithm for solving this path for weighted graphs. All right. Thank you, everyone, for coming. And, I'll see you next time.